Hi again, everyone. Dr. Tom McNamara here for our course in college algebra again. We are continuing our work with exponential functions. In the last video, we went over an important application of the exponential function to compound interest. And we went over these two formulas here. This formula was for things like compounded daily, weekly, monthly, quarterly, etc., where you had a specific number of times the interest was compounded each year. And this second formula was for continuous compounding. Okay, so we're going to do a couple quick examples of those and then maybe hit you up with some other examples as well. So let's switch over to a set of problems here. Let's turn off the document camera and go to this. Make it nice and big so we can see it. Okay, looks good there. Okay. So the problem asks us to determine the final value if we have $1,600 at 11.8% interest compounded monthly for 1.5 years. All right. Easy enough. Compounded monthly means we're going to use this form with n equals 12. Okay, let me switch back to the document camera so you can see what I'm writing here. So we're going to use this formula with n equals 12, and the final amount would be 1,600, which was our starting amount, 1 plus 0.118. Okay, so I have converted my 11.8% to the equivalent decimal, divide that by 12, and my exponent is 18. How did I get the 18? Well, I took the time in years, which was 1.5 years, times 12, which is exactly what this formula says to do. Okay, and that gives me 18, which is what my exponent should be. And now I enter this pretty much exactly as it looks on this calculator. 1,600 times, open parenthesis, 1 plus 0.118, divide by 12, close the parenthesis, exponent 18, enter. Okay, so I end up with $1,908.16. You'll notice that I rounded my answer to 2 decimal places. Whenever you're dealing with money, the smallest amount of money we have is a penny, so that's the rounding you should do. Okay, let me go back and check, see if I got the right answer here. We'll turn that off, we'll go back here. So I believe we said we got $1,908.16. We'll go over here and check our answer. Okay, great, we got it. We did a correct application of that formula. Okay, looking at this, we can see here we're supposed to use the compound interest formula to determine the final amount. Once again, this is $1,400 compounded continuously for 11 years. Okay, so since we see that magic word, compounded continuously, that means we're using this formula. So, in this example, we'll have 1,400 E. Remember, E is a special number that you can get on your calculator. I'll show you how to do it in just a sec. And the interest rate was 7% times 11. 0.07 times 11 is 0.77. I always recommend you do the exponent in a little side calculation. So 0.07 times 11 equals 0.77. That's why I'm using that for my exponent. All right, now how do I enter this? Well, I do 1,400 times second ln. All right, you see right there? Come on, camera, focus, focus. I don't know if you can see it that well. Okay, right above the ln button, there's a little tiny e to the x. Okay, that's how you get that function there. E to the 0.77. So you do second ln. And then we just enter that exactly like it looks, equals. Okay, so we are getting $3,023.67. Okay, so let's go and check and see if that agrees. All right, nice. Okay, so the rest of these compound interest problems can be done in very similar ways. You just have to pick the right formula and use the right numbers in those formulas. Okay, so how do you tell which one to use? Well, if the problem says compounded continuously, use this one. If it says compounded daily, weekly, monthly, annually, semi-annually, quarterly, use this one with the appropriate value of n. Now there is another kind of problem in this exercise set that I wanted to talk to you about. Okay, and it's this type of problem right here. Let's go to the window capture again. Okay, so we have a sample of bacteria where there's initially 2.6 million bacteria per milliliter, and its concentration doubles each week. Okay, so we're supposed to find an exponential model that calculates the concentration, and then we're supposed to find out what the concentration of bacteria is after 1.1 weeks. Okay, so this actually goes back to a model that we saw not so long ago. Okay, and the model was this. F of x equals c a to the x. C was always our starting value when x equals 0, and a is kind of like the growth factor. Okay, so in this example, we are starting out with a concentration of 2.6 million bacteria per milliliter. So I'm just going to put 2.6, and we will realize that the whole thing is measured in millions. Okay, 2.6 million bacteria per milliliter, and then 2 to the x. Now, why is it a 2? Because in the problem they told me the bacteria concentration doubles every week. So the first week goes by, I double. The second week goes by, I double again, which means I'm now multiplying by a factor of 4. 3 weeks go by, I double that, which now means I'm multiplying by a factor of 8. So it's powers of 2 that matter. So let's go to my math lab here and check. It says we're supposed to type an equation. B of x equals 2.6 times 2 power x. Okay, so 2.6 times 2 power x. Check that. Got it. Wonderful. Okay, so that's the model. And I do want you to notice something. It's not like we have one model for this and one model for the compound interest. It's the same idea. Starting amount, and then you have this growth factor. Okay, so for each, in this case, each month that goes by, you have this percentage increase tacked on. You got to do 1 plus because you keep everything you had plus that additional stuff. So really the same type of situation here. Starting amount, and then an exponential function over here. Okay, so let's go back and answer this next question. The concentration of bacteria after 1.1 weeks. Well, if we go back to our model, x represents the number of weeks that have gone by. So they're telling us 1.1 weeks have gone by. So we do 2.6, nope, not 26, 2.6 times 2 power 1.1. Okay, so round to the nearest integer as needed. Okay, round to the nearest integer as needed. I'm guessing that'd be a 6. Okay, let me go back to the window capture so you can see I actually got it there. Okay, so it is 6 million bacteria per milliliter, and that's that. Now, one more Okay? I don't want you to get tripped up on a problem like this. Okay, so this says fish fly density is 3 million insects per acre and is decreasing by 20% every week. Okay, now we want a function that tells us how many fish flies we have, not how many fish flies we don't have. Okay, so our model is going to look like this. F of x equals 3. Okay, 3 was the starting amount, and we're realizing this is 3 million insects per acre. And then we got to realize, okay, what is it we have left? If we lose 20% of the insects in a week, then we keep 80% of the insects. So this will be our function where x is the number of weeks that have gone by. Okay, now the problem asked me to find the density of the insects after 3.4 weeks. All right, so all I do is I plug 3.4 into my function. Okay, so which we've got written right there. So 3 times 0.8 power 3.4. It was 3.4 weeks later, equals. Okay, so I'm getting this. Okay, now it makes sense in this case that the density is less because remember we are losing insects here. It says in the problem that the density per acre is decreasing. Okay, so we should expect to get an answer that is lower than the starting value. Okay, and the problem said round to the nearest hundredth as needed. All right, so 1.40. Great. Okay, so exponential models. Okay, very simple setup to understand. You have your starting amount times and then your growth or decay factor raised to an exponent.